Hello, my name is Malaquías Peña, and I'm presenting this paper, Satellite Altimeter Data for Offshore Wind Energy Applications in the New England region. My co-authors, Chimbali, Panagiotis Mitsopoulos, and Eugene performed the analysis and created the figures that I'm presenting today. To give you a little bit of a background, why the southern New England region. As you could see here from the Bureau of Ocean Energy Management maps, this is in colors are the list areas, and you could see a high concentration of companies planning to develop offshore wind energy projects in the area. So why there? Well, the facilities are conveniently located near the centers of demand. Another reason is that the area has a wind surface that exceeds 7 meters per second in the annual average of analysis of historical data, which guarantees that there are enough wind energy resources in the area. There are other drivers. Some of them are related with the fact that the wind turbine designs are making less expensive the generation of energy. There are some estimates of wind energy even going to be lower in price, and here some references are the levelized cost of energy, which is less than approximately less than the energy generated through gas. Other motivations are the increasing price of electricity in the area, and also at the state level, all the states have new regulations and goals related to reduce fossil fuel gases due to that impact climate change. The data in this analysis is mostly the Saral Altika level 2, which is after quality control. Here you see in colors, in red color during the second phase, which is the drifting phase, and in blue when during the first few years when the track was fixed. Now, as you could see, the temporal resolution along the track is relatively high. The repeat cycles, that means how many days it takes to get to the same area, is 35 days in the Saral Altika, 10 for Jason 3, and so on. So they have different resolution or footprint, Ka and Ku, and different periods of data. So we combined in some of our analysis, but mostly we focus on the Saral Altika data, as I said. If we were to collect only the data that occurs within 2 passes of the Saral Altika, we would see the observations that are collected in 35 days. You see the different colors represent the satellite measurements. Now, how we do the validation of Altika data with in-situ observations? We also collect in-situ observations from buoys and from wind towers. The BOSM-3 is an offshore wind tower. And then we select the most representative radius that has enough sample size. So here is a plot of our calculations of radius. A larger radius would mean the higher sample and the bias. So by looking by eye, we decided to go with the radius of 0.27 degrees, which is about 0.25 degrees, which is about 27 kilometers. So here is I'm showing one case, that's a representative case of buoy 4497, which is in the open ocean. On the left is when the radius is about 27 kilometers, and you could see that the number of cases is fewer compared to the ones on the right, but they tend to fall within the 1-1 diagonal line. On the right, we see the number of satellite overpasses the circle between 27 kilometers to 55 kilometers. So these two figures together indicate the trade-off between increasing the sample and maintaining the decent low systematic errors. If we use a 27 kilometers radius, we could see that the significant wave height is highly correlated with the between the Altika and the buoy data. More interesting is that or maybe expected that the correlation is higher for the three stations, three buoy stations that are in the open ocean, whereas those that are within the Long Island Sound are not as accurate, especially the one on Western Long Island Sound. So here in this table, I'm showing the correlation and also the root mean square errors in meters. So we're talking about 12 centimeters, 12 to 15 centimeters in the root mean square errors. Now for the wind speeds, here the scatter plot tend to be much higher. The distribution, the standard deviation of the distributions tend to be higher. The other thing that we notice is that the errors tend to be larger. The shaded area, by the way, is the 99 level of confidence of the blue line, the regression line. We also can notice two types of systematic errors. One is the mean, we call it mean systematic errors, which is in parallel to the diagonal. But we could also see that the slope or the proportionality is biased. So these are the two types. Still, the errors tend to be sufficiently small to make the analysis. Now here is the correlation between the estimates from the Altika sensor and the observed wind. As you could see here, we don't see the same contrast between open ocean and stations that are in the Long Island Sound, but we see something like an anomaly here, that the BOSM3 stations the time series tend to be smaller than the rest of the stations. Now, once we have a characterization of the properties of the wind, we would like to be able to compute the energy density and the estimated power output based on observations and also with the overpasses of the altimeter altimeter sensors. If we let me explain here what are these circles. So this is the BOSM3 station that provides every data every hour. This is our target domain, which we would like to estimate. And here on the western side, we see a wind farm, which is the Block Island wind farm. We would like to, or we did, borrowed the power curve from data from here and applied to the area in the red circle. So in the top right is the power curve, which we use to generate the lower right panel hot map, which shows changes in the season and also changes in the diurnal variability. So the stronger signal is in the seasonal, whereas the diurnal, it's not well it's not doesn't appear in this the signal is not sufficiently strong for this at least for this sample period that we are using. On the left, it's a plot of 10-minute average of data, surface 10 meters wind data for various for winter and for the summer. But one of the issues that we need to confront is what function should be the most suitable, the most appropriate to the data. So we used generally the Weibull and the Rayleigh functions to do our calculations. Here is the energy density on the target area, which is the green box that I just showed. And here we could see the Saral Altika data on the top and the bus M3 hourly data on the right. When we plot the scatter plot and fit a line, it looks like this. So there is a strong proportionality bias which needs to be taken into account to generate the new Weibull distribution. Once we have the parameters, the two parameters of the Weibull distribution, one can substitute in the energy density, and when we do that, we get values in the range of 340 and 360, which is in the range of what is shown here in this white circle. So to summarize or to conclude, this study validates the altimeter data from the Saral Altika. We found that the significant wave height estimations are accurate, and that means that the root mean square error is small, and that there is a high temporal correlation with the buoy observations. There are some small systematic errors, but in some stations near the coast, especially those that are inside the sound, have much larger errors. Surface wind estimations are highly correlated as well with the buoy observations, but they tend to have a wider spread, and they have larger systematic errors. We talk about two types of errors. One is the mean errors, and the other is the proportional systematic errors. Another conclusion in this study is that it's possible to estimate the power output of a hypothetical wind farm if we utilize the power curve derived from the Block Island wind farm data. We use that, and we created the hot map that I described. We noticed that there is a strong seasonality in the power output, and there is a small diurnal signal. So when we combined both the in situ and the remote sensing data, we get a much better estimation of the energy density in the area. The values that we got are consistent with previous studies. Thank you.